First of all, welcome everybody to join today's webinar. Today I am excited to introduce a new friend to you. So Dr. Ba, who is currently an assistant professor at the University of Pittsburgh. So formerly she was a PhD in economics at UPenn. So today's work will be sort of at the intersection of the behavioral science and the cognitive science. So actually, there is a lot of common research interest among the both communities, among which something like, the cognitive resources such as attention, memory, and even the computational power of the human brains. So how could people allocate, optimally allocate those kind of scarce resources? And there are actually a lot of interesting phenomena during such a process when people trying to optimally respond to the newly occurred information and trying to economize of their allocation of their scarce cognitive resources. So I'm super excited to hear about today's work, and I believe that Cuimin will also cover a lot of applications, especially those on the financial industries, right? So let me stop here and give the rest of time to Dr. Ba.
Okay, thank you very much, Feng, for your invitation and introduction. I'm really happy to present this joint work with Aislinn Boren and Alex Rimas. And this paper is titled Over and Under Reaction to Information, the Impact of Complexity on Belief Updating. And before I go into details, I first want to, spoiler alert, there's nothing that's super, so this is not a rationally attention paper. It's not about rationally allocating resources, more about when there is a limit on mental resources, how people respond to that and how that distorts their belief updating. So with that, let me get started. In this paper, we explore a fundamental question: how do people react to information? So we know that the standard model in economic theory often assumes that people have an accurate mental representation of the learning environment, and then they use the Bayes rule to draw inference with respect to this representation. But at the same time, there is a large literature in economics, finance, and psychology that documents departures from this standard model, and sometimes those departures are systematic. But here's the challenge. The literature presents some quite mixed evidence on the direction of the bias in belief updating. For example, here I have a collection of papers studying this question, and here we see some papers documented people underreact to information as compared to the Bayesian benchmark, while other papers find that people overreact to information. And if we break this down and look at this closely, the direction of the bias seems to be dependent on where the data comes from. So for example, Benjamin 2019, this is a comprehensive meta-analysis of past experimental work. And he said that the experimental evidence on inference taken as a whole suggests that even in small samples, people generally underinfer rather than overinfer. But on the other hand, Bordello, Giannoli, and Schleifer and Mao provide this very nice review of evidence outside of the lab, particularly in the financial markets. And they said that expectations of professional forecasters, corporate managers, consumers, and investors appear to be systematically biased in the direction of overreaction to news. Okay, so of course, there are a few exceptions to both these observations, but this divide exists in the big picture. Okay, so a natural question is, how do we reconcile these findings from the literatures? Can we provide a unified explanation for them? So to answer this question, in this paper, we develop a model of belief updating to capture how agents respond to complexity with finite mental resources like attention and processing resources. And we show that the cognitive constraints on these resources, they are going to interact with the learning environment to systematically distort beliefs in the directions that we can predict. In particular, our model is going to generate a rich set of testable predictions on how people's reactions can depend on the properties of the learning environment. And in particular, our model is going to predict that people are going to react in different ways depending on the learning environment. And they're going to overreact if the state space is complex, the prior is concentrated, and if they're facing signals that are noisy and disconfirming their prior. And they're going to underreact if the state space is simple, the priors are diffuse, or the signals are precise and confirming. Okay, I'm going to go through this very soon. And this results on a very high level. Why are they interesting? Because this results or this mapping between properties of the information environments and predictions on over and underreaction, this can rationalize a lot of findings that we have in the literature, as I just covered. In particular, our results suggest that the predominance of underreaction in lab studies and experimental work, this could be a result of the focus on simple binary state space and very precise signals. In contrast, the overreaction in financial markets and in macroeconomy, this could be because of the much richer, complex state space and much noisier signals. And in fact, the very few experiments in the lab that have found overreaction all feature information environments with a lot of states or very noisy signals. So the takeaway is that, contrary to what people think, the use of binary states in the behavioral lab, this was not without loss of generality. And given the complexity in the real world, in the financial market or or as a macroeconomy indicator, it's not surprising that overreaction to news in the real world could be really common. So here is the roadmap for today's talk. I'm going to walk you through a model of belief updating and our basic experimental setup. And then we're going to go through the theoretical predictions and also the experimental results, iterating through the predictions. And depending on how much time we have left, we can cover some additional analysis, some of which provide direct evidence for the proposed psychological mechanism, and others assessing how well our model fit the data. Okay, so that's a quick overview of the paper. Now let me take a couple minutes to sketch out some core ideas of our model. Okay, so let me be very slowly on this part. In our model, we have an agent who faces a belief updating problem. Okay, she wants to learn about an unknown state of the world, omega, that can take one of n possible values. So it could be omega 1, omega 2, omega n. Okay. And all of these all of these states are within the range of 0 and 1. So for example, you can think of this agent as an investor who is learning about the underlying quality of a firm. And this company could be a really bad, it's a zombie type of company that's about to get bankrupt. Or it could be a really successful unicorn company like Google or Apple, okay? Or it could be something, some intermediate type that falls in between really, failing company and really successful company. And our agent has a prior belief about the state, about the quality of the firm, and this prior is denoted by P0. And then our agent, our investor, is going to observe a binary signal about the state. So here we assume a binary good news or bad news structure, where the probability of seeing a good news signal or a bad news signal, this is changing monotonely with the state. So specifically, the signal could be either good or bad. The probability of seeing a good signal conditional on state omega is increasing omega. In fact, it's just given by omega. Okay. And the probability of seeing a bad signal given state omega is just 1 minus omega. So for example, it's more likely to see a good news, such as, see price increase, a stock price increase, if the company has higher quality, right? So as the company shifts from a zombie type of company to a unicorn type of company, the probability of seeing a good signal increases with omega, and eventually becomes 1 if the firm is a unicorn type. Okay, so this is a simple state belief updating problem. From the prior and the signal structure, we can derive the objective posterior belief from the base rule. So this is just the base formula. The posterior probability of state omega given the signal realization S, this belief denoted by PB is just given by the joint probability of state omega and observing signal S, and over the marginal likelihood of signal S. Okay, so base rule, super simple. If you know that, problem solved. But our agent doesn't necessarily know how to do it. Instead, we model belief updating as a two-stage process. In the first stage, our agent forms a mental representation of the information environment here. And this representation is not necessarily accurate because of the representational complexity here. What do I mean by that? I mean, as the number of possible state increases, so as n increases, our agent, in order to form beliefs, she needs to keep track of more and more objects to form an accurate representation of parameters here, right? Because there are more potential states values, there are more prior probabilities, there are more conditional probabilities to remember. So limited attention and working memory constraints are going to push the agent to simplify the learning environment by focusing on states that are more salient. So this is what we have a lot of psychological evidence on. And what does that mean, right? Attention channels to salient states. Essentially, salient states are the states that stand out. And operationally in our model, this salience is captured by this R function. Okay, so this is the previous signal structure, but now the perceived signal structure, the perceived information environment is distorted by the salience of the states. So this R function measures how much a state omega grabs your attention given a particular signal realization. And the parameter theta here is a parameter that scales the magnitude of this distortion. So this salience function affects the perceived information environment in this way, and is going to cause salient states to be overweight in her representation. Okay, because if R is larger than 1, then the signal is going to be perceived as being occurring with higher probability at this state. But now, which states are salient? This is the critical part. Can we put more structure on what is salient? Do we know which states are salient here in a particular information environment, right? So it turns out we can, because there is a ton of evidence in psychology and economics that people tend to focus on things that are representative in their environment. Now, what does representativeness mean? So in our setting, this representativeness, the salience function that captures representativeness, implies that the state omega is more representative if it is more likely to generate the signal that the agent observes. All right, so this conditional probability of observing the signal S given omega is the highest. Practically, for example, when the agent sees a good signal, okay, like a stock price increase, the highest state, the unicorn type of company, is the most representative of that state, of that signal, right? Because this state is the most likely to generate, under that state is most likely to observe a good signal, okay? So as a result, the agent is going to overweigh the probability of the company being a unicorn. Now, this is not a top-down type of rationaling attention. This is more sort of a bottom-up attention allocation due to the stimuli in the external environment. On the other hand, if the agent sees a bad signal, like a price drop, a price decrease, then the lowest state, the zombie type of company, is the most representative. So our agent overweights the possibility of the company being a zombie and becomes pessimistic. Okay, and now let me mention that although we focus on this representativeness as the primary cue of salience, our model is quite flexible in that we can vary this R function, and so we can incorporate other types of salience cues, and we're going to explore that in the additional analysis. But that being said, we are going to provide empirical evidence that representativeness is indeed the dominant salience cue in our setting. Okay. So that's the first stage of belief updating in our model. After forming this mental representation, our agent is going to move to the second stage, actually process the information. So if the agent is sophisticated, then she's going to take the mental representation, pi hat here, and apply Bayes' rule to it and form this, a Bayes sophisticated posterior PR. Okay, but here our agent faces computational complexity because she needs mental resources to perform the relevant computation, the relevant calculations to actually process the signal and update her beliefs. But these resources are also limited. And so this is going to create what we call in the literature cognitive imprecision or cognitive noise, which means that the agent does not fully absorb the information, but absorbs the information with some noise. And to illustrate that, let's return to the investor example for a bit. Say the investor forms belief about firm quality from its stock price. And the key part here is that in different markets, there could be different probabilities for a price increase for unicorns, zombies, and intermediate types. And so a boundary rational investor may struggle to adjust fully to the given parameters of the particular market, right? And so the agent doesn't fully adjust to the given parameters, and instead she partially relies on the cognitive default that stems from her prior knowledge that serves as a baseline for her beliefs. And this is we take this cognitive default as an ignorance prior in our model, which we also provide empirical evidence for. And this implies that shading towards this cognitive default is going to dampen her response to changes in the probability of a price increase relative to a cognitive precise investor. So coming back to the model, we denote this cognitive default as P0 bar, and we assume it's the ignorance prior or the uniform prior. And the final subjective posterior, denoted by this P hat, is going to be a combination of the cognitive default and the actual posterior derived from the mental representation using Bayes' rule. And this parameter lambda here is the weight attached to the actual parameters, and this is going to decrease if the agent is more cognitively imprecise. Okay, so our analysis will focus on this agent's final subjective posterior. As you can see, this is shaped by both the representational distortions from the first stage and also cognitive imprecision from the second stage. And so together, their interaction is going to generate a super rich set of patterns of over and under reaction, depending on the structure of the information environment. Okay, so to talk about underreaction, overreaction, let me first define a proper measure of that. We say that the agent overweight a state given signal realization S if her subjective posterior P hat attaches a higher probability to this state relative to the Bayesian posterior. Okay, and she underweights it if the probability is lower. And to measure the agent's overall reaction, right? This is her reaction to a particular state. We're going to measure the agent's overall reaction. So we're going to compute the subjective expected state. So just take an expectation of the state using your subjective posterior or the objective Bayesian posterior. And we denote them as E hat and EB separately. And then we're going to look at the difference between the subjective movement in expectations and also the objective movement in expectations. We're going to look at the difference between them, and we're going to define this overreaction ratio as this difference normalized by the objective movement in expectations. So this means that if the ratio is positive, right, so then the agent exhibits overreaction because the agent moves her subjective posterior more than she should be. So she overshoot. And if this ratio is negative, we say that the agent exhibits underreaction. So this measure is capturing how much the agent reacts average across all states. And this allows us to compare the agent's updating patterns, updating biases across different information environments, where the Bayesian movement of beliefs could be different. Okay. So that's the model.
Sorry, did you rule out the possibility for going to the wrong direction here?
Yes, for sure. So first, for simplicity, I omit that. But in the paper, we define underreaction as the case of R being negative but larger than -1. But if R is so small that it is below -1, then this is the case that the agent goes basically in the opposite direction as EB moves away from the prior expectation. So in that case, we say that the agent updates in the wrong direction, and we also separate our data analysis and if I have time at the end, I can talk about that. But basically, the insights are very robust if we take out the observations that agents updates in the wrong direction or include it. Okay, so so I haven't talked about the theoretical predictions and the results yet, but before I do that, let me quickly walk you through our experimental setup, and so you can quickly see how our experiments mirror the theory closely and how we can test the theory. Okay, so in our experiments, we use a classic balls and urns design. This is very common in the experimental literature. So imagine there are 100 different cards. 50 of these cards have earn A written on them, and 50 of these cards have earn B written on them. Okay, now you don't know which card has been drawn. Nature is going to draw a card. You don't know which card has been drawn, but that card is going to determine which urn will be used next. Okay, so if it's earn A card, earn A is going to be chosen, earn B card, earn B is going to be chosen. Now, each of these urns, they contain 100 balls, which can be either red or blue. Urn A contains 70 red balls and 30 blue balls. Urn B contains 30 red balls and 70 blue balls. So urn A is more red than urn B. Okay. Now after and then we draw a ball from the chosen urn, but you don't know which urn has been chosen, remember? But we show this ball to you, okay, it's a red ball. And then we ask, what's the probability that urn A was chosen in the first step? Okay. All right, I'm going to give you a time's up. So I'm going to tell you the correct result. So if you use the Bayes rule, we can use the Bayes rule to calculate this Bayesian benchmark. Okay, so again, this is prior probability of A, the conditional probability of seeing a red signal given A, and then the denominator is the marginal probability of seeing a red ball. Okay, so if you do this, the calculation is very simple. The conditional probability of urn A, given that we see a red ball, is just 0.7. Okay, so we increase the probability of urn A from 50% to 70%. Because the urn A is more red, right? So observing a red ball is more indicative of urn A. Okay, so although this Bayes formula is very simple, as we go through in the theoretical setup, this Bayes rule has captured all relevant all components of the information environment that are relevant for belief updating. So first, here we have two urns, okay? So we have two possible states of the world, A or B. So complexity of the state space is just two states. This is a pretty simple structure with only two states. And the second component is the prior. So we have a uniform 50-50 prior. Why? Because we have 100 cards, 50 for urn A, 50 for urn B. So the ex-ante probability of drawing an A or an B is 50-50. And third, we also have the signal diagnosticities. And these are referring to the conditional probabilities of seeing a red ball or a blue ball, a red ball given state A or state B, right? And these are determined by the urn compositions, right? So this is a paradigm that's very classic because it's very transparent to manipulate the components of this information structure. And it has been used to study a broad set of learning settings. And what we will do in this paper is that we will build on this paradigm and we will vary these components of the information environment to see how people react differently, whether they behave differently as predicted by our theory. So we run a pre-registered experiment with over 3,800 participants on an online platform called Prolific. And before the experiments, participants have to pass a series of attention and comprehension checks to make sure that they understood the setup. They answer between 8 and 15 questions, each in random order. And we pay a $2 base fee for their participation and a $10 bonus if their randomly selected answer is within 3% of the base and posterior. Okay, so our participants, they're incentivized to try their best to guess the correct posterior. And in those 8 to 15 questions, they're going to face different belief updating problems that could vary in terms of the following three aspects. So we vary the complexity of the state space, we vary the signal diagnosticity, we also vary the prior distribution in terms of its flatness and symmetry. In particular, we vary the complexity of the state space by just increasing the number of urns. So previously I showed you that there are just 2 urns, but in our experiments, we can possibly have 3, 4, 5 urns. And here is an example with 3 urns, okay? And we also vary the prior distribution, which is determined by the card composition. For example, here we give more cards, 50 cards to urn B, so this creates a prior that's more concentrated on the middle state. And finally, we also control the signal diagnosticity by changing the proportion of red versus blue balls in each of these urns. And basically, the more different the ball composition is away from 50-50, the more diagnostic of the signal for that state. If it's 50-50, right, then the observing a ball is not informative at all about that state. Okay, so one thing to note is that because here, as in our theory, because the signal follows a binary good news and bad news structure, the most representative state is always an extreme state. For example, if a red ball has been drawn, then urn A is the most representative state. Why? Because urn A contains the most red balls. And if urn C, if a blue ball has been drawn, then the most representative state is urn C, right? Because C has the most blue balls. Okay, so now that we have seen both the model setup and also the experimental setup, we're ready to look at the theoretical predictions and the experimental evidence. So let's start with our first prediction, which is about complexity. So let's fix 2 information environments, omega p0, omega prime p0 prime, with symmetric state spaces and uniform priors. So by symmetric, I mean that if state omega I is in the state space, then 1 minus omega I is also in the state space. So this is for technical simplicity. So it just means that for a good state, there is also a symmetric bad state in that's possible. And we're going to let this R to denote the overreaction ratio for the first information environment and R prime for the second information environment. Prediction 1 says that if we fix the most salient state and the least salient state, so we fix the extreme states such that the dispersion of the state space stays the same, and we just add in more interior states to omega to create omega prime, then when the extent of its representativeness is large enough, then which means for sufficiently large theta, our agent is going to overreact more if the state space is more complex. Okay, so let me quickly tell you the intuition for this. So why is that? So say that we start from a market with only zombie and unicorn type of companies. Okay, when the signal arrives, because this state space is so simple, there's not much to simplify. So the mental representation is more accurate, is less distorted. So it's the processing stage, it's the processing distortion that's driving the agent's reaction, right? And then because our agent, because of her noisy cognition, she shades towards the cognitive default. And with that, she tends to be underreacting. However, if representational complexity goes up, say that we move from this market with only 2 types of firms to a market with a whole range of intermediate firms, then what would happen is that there is a larger distortion in the mental representation because there is a much larger scope in overweighing the most representative state at the expense of underweighing all other non-salient states, right? So for example, if we observe a price increase, this is a good signal. Is representative, the state 5 is the most representative, and so we can overweigh it. But when we have more states, we have more room to overweigh state omega 5. Okay, so if salience is driven by representativeness like this, the agent is going to overweigh the extreme state that the signal is pointing to, and as a result, the agent is going to overreact more. Okay. Now, by a very similar logic, we also predict more overreaction for noisier signals and more underreaction for precise signals. The intuition is very similar. For noisier signals, there is a much larger scope for the agent to distort the mental representation of the signal structure. Okay, so to test this prediction 1, we increase the complexity of the state space, and we see how people's reported subjective posteriors change. In particular, for the two-state condition, the state space only consists of x and 1 minus x, where x can take values like 0.6, 0.7, 0.8, 0.9. Okay, so remember, these are the state values that are also governing the conditional probabilities of seeing a good news signal given the state. Okay, now for the three-state condition, we just added 0.5 to the state space. And for the four-state condition, we add y and 1 minus y, where y is more interior than x. That can take values from 0.55 to 0.8. And we can continue this process to create a 5-state condition by adding another 0.5, and finally a many-state condition with 11 states ranging from 0 to 1. And throughout these conditions, we are going to keep the prior uniform. Okay, now let's look at some results. So here's what we found. First of all, we replicate the standard result, the classic result of underreaction for binary state space. Okay, so when there are only two states in the state space, when we calculate the fraction of people, the difference between the fraction of people who overreact and the fraction of people who underreact, this difference is significantly below 0, meaning there are more people underreacting versus overreacting. Okay, and the pattern is similar if we look at the overreaction ratio breakdown. So here, the horizontal axis is the signal diagnosticity for the highest state. So this is just x times 100. And vertical axis is the overreaction ratio. So across all signal diagnosticities that we have here, we get underreaction. And this is consistent with the prior lab findings of underreaction. But now it's when it gets really interesting. As soon as we add in one more state, okay, make it 3 states, the majority of participants begin to overreact. And there are even more people overreacting as complexity goes up. If we look at the breakdown across different signal diagnosticities, we see that the participants' overreaction ratio moves completely from below 0 to above 0. Okay, this red curve here. And on top of that, we observe more overreaction as signals become noisier. So as this X moves away from the extreme 0, 100 to 50, 50, which is totally uninformative, agents, the participants, they exhibit higher overreaction. This is also consistent with our other prediction. And if there's going to be even more overreaction as we add 2 more states to make it 5 states. So what does this all mean, right? So we have observed that there is underreaction for binary state space, overreaction for more than 2 states, and there's even more as we go up. So taking stock here, these results help us organize a lot of conflicting evidence in the literature, because nearly all lab experiments use binary state space because they think it's a good abstraction of the real world. So our model predicts underreaction for this type of state space, right? So with 2 states, representativeness has little bias, so underreaction is expected. And the very few experiments with more than 2 states, they do find overreaction, which our model also predicts. And if we turn to financial markets and the macroeconomy, large state spaces are the norm. Because the state, the underlying quality of a firm, or how the possible inflation rate. So here you have a lot of uncertainty, and oftentimes states are not just good and bad. They form a huge set or even a continuum. So if people simplify these state spaces and channel their attention to representative states, then overreaction becomes much more likely. And our findings are also consistent with other evidence that, forecasters, they overreact to long-term indicators and underreact to short-term indicators. This makes sense because for the long term, you have a noisy signal. For the shorter term, you have more precise signal. So this is also consistent with our theory. Another prediction here says that if we fix the state space in the information environments and just vary the prior, okay, and we assume the priors are symmetric, and if the prior is more concentrated, which means the prior assigns higher probability for states in the middle, then again, for large enough theta, the agent overreact more for the more concentrated in the middle prior. So the intuition is quite similar as before, because so when the prior is diffuse, or it puts a lot of probability on the extreme states, then even a Bayesian agent with that prior is going to put a lot of weight on the extreme states. So if you add representativeness on top of that, this representativeness-driven attention doesn't have much impact, right? But if the prior is concentrated in the middle, then as before, representativeness has a lot of bite because it attracts attention to the extreme state that receives a very few weights ex ante. So in that case, that's going to generate more of a reaction. And to test that prediction, we keep the state space constant. We focus on state spaces with only 3 states. And with this complexity condition, we experiment with a uniform prior, a concentrated prior that puts higher probability on the middle state 0.5, and diffuse prior that puts more probability on the extreme states x and 1 minus x. So here are the results. Starting from the uniform prior, this is the same pattern as before. Overreaction across all signal diagnosticities with more overreaction for noisier signals. So this pattern has been really robust. And then when we shift to a concentrated prior that puts 50% probability on the middle state, then putting more, this is going to generate more overreaction across the board, okay? And if we put more weight on the extreme states and we do 40, 20, 40, then we actually, so we have much less overreaction. And in fact, we have underreaction coming back for very precise signals. Okay, so in that case, we have both overreaction and underreaction here. Okay, so our third and also last theoretical prediction focuses on a type of signal realization. And I talked about what happens when the prior is asymmetric. Okay, so far we have been thinking about symmetric priors, meaning we have a uniform prior like 50-50. But let's now think about what happens if the prior is asymmetric, meaning that we can have, if we have a binary state space with just A or B, then the ex-ante probability of A could be higher or lower than the ex-ante probability of B. Okay, so we're going to focus on the binary state space here so that we can easily manipulate the skewness of the prior. So when the prior is symmetric, we can categorize a signal realization as being disconfirmatory or confirmatory, right? If our prior attaches higher probability to A, then the signal that's more likely under state A is confirming the prior, and it's going to push our belief even further to even further up for state A. Okay. Now prediction 3 says that the agent tend to overreact to disconfirmatory signals, especially if it's imprecise. On the other hand, for confirmatory signals, our agent tends to underreact to confirmatory signals, whether it's imprecise or precise. Okay, so the intuition of this prediction basically stems from the shading towards your cognitive default. Because if you have, say that if you're optimistic about the state, you have a prior that attaches higher weight to the good state, then you observe a disconfirmatory signal that make you less optimistic. Then by shading towards the ignorance prior, you're pushing yourself to being even less optimistic, right? So in that case, you're overreacting to this disconfirmatory signal. While if it's confirming your prior, making it further optimistic, then by shading towards your the ignorance prior, you're underreacting to that, to the signal. Okay, so to test this, we use the binary state space and we manipulate the relative direction of the signal. So we start with a uniform prior 50-50. We introduce two asymmetric priors. One puts 70 probability on 1 minus x, the other puts 70 probability on x. Okay, so when we categorize people's reactions based on the direction of the signal could be neutral if the prior is 50-50, right? Because there is no disconfirming or confirming signal. When the prior is asymmetric, we can say the signal is disconfirmatory or confirmatory. So what we found is that there is substantial underreaction to confirmatory signals, as indicated by this green curve here, in contrast to substantial overreaction for confirmatory signals. And this is consistent with our prediction. And all of them are in contrast to the mild underreaction to neutral signals. So receiving a confirmatory signal really amplifies the underreaction here, and receiving a disconfirming signal shifts the reaction from underreaction to overreaction. Okay, so far our experimental results really strongly support our predictions about the patterns of over and underreaction. But you may say, okay, this could be because how you're measuring the overreaction underreaction, right? There could be potential issues with just looking at the overreaction ratio. Of course, we also look at the fraction of people overreacting or underreacting. But there are potentials with the overreaction ratio because this ratio has a particular functional form. It has a particular parametric structure. And as we are moving across different information environments, we're comparing across them, we're also changing the Bayesian benchmark. So we're changing the normalization factor in the overreaction ratio, which you may argue could be driving all these results. So to address all these potential problems, we can take a different approach. We can examine the model predictions on the whole belief distribution of beliefs and see how the agent react to each of these states. Okay, so this approach is completely model-free. There are no parametric assumptions about the data. There is no parametric assumption about the measure. So what we do in this part is that for each individual state, we look at the difference between the model subjective posterior and the objective Bayesian posterior, okay, to see how our model predicts differently from the Bayes rule. Okay, and we're going to look at three groups of states. We're going to look at the least representative state, the most representative state, and all of the middle states pulled together. With the vertical axis here is just this the belief difference between the subjective posterior and the Bayesian posterior. Okay. So if people only exhibit representativeness channel attention, so people only go through the first stage, they form a distorted mental representation, but they're very sophisticated in processing information, then such a model is going to predict that the most representative state is overweight at the expense of underweighing all the other non-representative states. Okay. Now, if people only exhibit cognitive imprecision, so if people only go through the second stage, they have a perfect mental representation, but it's just that they in processing the signal, they shade towards the cognitive default, then that is going to predict a dampened response to information, right? So this means that the most representative state would be underweight relative to the Bayesian posterior, whereas the least representative state will be overweight relative to the Bayesian posterior, and the middle states as a whole are neither over or underweight because any force would be completely canceled off. But in our two-stage model, what's magical about our two-stage model is that the interaction between channel attention via representativeness and cognitive imprecision, they're going to create a unique pattern of how you're reacting to these states. So in particular, our model predicts that the most representative state will be overweight the most, consistent with representativeness only model. But at the same time, the least representative state can also be overweight because of cognitive imprecision. Okay, so you can see that the first graph combine the second, add up the first two paragraph of the first two graphs, create a third graph. Okay, what does the data look like? It looks really like the prediction of our two-stage model. Okay, so this is the data prediction. So it really matches the two-stage model well, with both extreme states overweight and the middle states underweight a lot, and also the most and least representative states both overweight. So this exercise really tells us that the belief updating patterns, they cannot be explained by representativeness only model or cognitive imprecision only model. And actually both types of models are really common in the literature. And rather, this belief updating pattern we're documenting here is a unique feature of the two-stage interaction in our framework. Okay, so we have seen a lot of experimental evidence that neither a single psychological mechanism like noisy, like cognitive imprecision, or representativeness alone can fully explain. That's why we need a two-stage model. But how can we quantify the explanatory power of our two-stage model? So quite fortunately, we have two excellent papers by Drew Freudenberg and Annie Liang that provide methodologies that allow us to measure both the completeness and also the restrictiveness of our model and allow us to compare our model with other models in the literature along these two dimensions. So completeness helps us understand how much value the two-stage model added as compared to the one-stage model, for example. And restrictiveness helps us understand how much more flexible we're making the model by adding a second stage. And both these measures, they range from 0 to 1. So I'm not going to go through the details of how to calculate them because of the time limit, but on a high level, completeness is a measure of the explainable or predictable variation captured by the model relative to an alternative, which we take to be the Bayesian benchmark. So this means that, so let this kappa be completeness. If a model is 0% complete, this means that our model predicts no better than the base rule. So our model captures no additional predictable variation as compared to the base rule. If this measure is 1, this means our model matches the best possible mapping exactly. So it captures all of the predictable variation. We estimate this best possible mapping using machine learning. Okay, so this completeness measure is different from a measure like R-squared because R-squared captures the overall fit of the model, including noise. So R-squared captures both predictable variation and also unpredictable variation that arise because of intrinsic error, intrinsic noise, or limitations on the data that even the best possible model cannot explain. So that we want to net out. We only want to look at the predictable variation. On the other hand, restrictiveness measures how flexible a model is. So specifically, let's say we draw 1,000 mappings between information environments and posteriors. And these posteriors, they are randomly drawn, so they look nothing like what a real human would report. Okay, restrictiveness is the ratio of prediction error on this randomly generated belief data between a model and the base rule. So this ratio, this restrictiveness ratio rho is 100%. So the model is 100% restrictive if our model fits this randomly generated data no better than the base rule, and 0% restrictive if it fits this randomly generated data perfectly. So ideally, we want a model to be highly complete, but also highly restrictive, right? Because if it's not restrictive, it's fitting this randomly generated data perfectly, which means that our model is not captured, it's just picking up random patterns in the data, explaining even beliefs that look nothing like what a real human would do really well. So we want a model to be complete and restrictive. That way, it captures our model captures important regularities in people's beliefs without being so flexible that it can explain everything. So our first result here is that the cognitive noise model is fully complete in the binary state space. So adding this mental representation stage, making it 2-stage, does not further improve the model performance. And this can explain why a lot of previous experimental literature, they have focused on noisy cognition and similar theories, because they do explain the data really well. So there's no reason to really explore other types of models. But when we go beyond 2 states, so there are 3 states or more, then the picture changes a lot, because the completeness of the cognitive noise only model now drops to only 36%. And by adding the mental representation stage, our 2-stage model has a completeness of 92%. Okay. Now, you may notice that in both cases, the completeness of the representativeness only model is just 0. Because if representativeness is the only bias that you allow subjects to exhibit, then they're going to exhibit no such bias. So this model predicts the same as the Bayes rule, which is the benchmark. That's why it's 0. So on top of completeness, that's just completeness, we can also compute restrictiveness. And together we can draw this kind of completeness restrictiveness frontier to see how much completeness you gain and how much restrictiveness you lose by adding parameters. So the horizontal axis here is completeness, the vertical axis here is restrictiveness. The Bayes rule, as well as the representativeness only model, is highly restrictive. Right, it has restrictiveness of 1, but it's also highly incomplete because it has a completeness of 0. Okay, so it's up here, so it's on the extreme end. The cognitive noise model, which did this purple dot here, so it's still highly restrictive, which is good, but it's somewhat more complete than the Bayes rule, but not too much more complete. Whereas our 2-stage model? Our 2-stage model, this red dot here, is really standing out because it loses just a little bit of restrictiveness, okay, and it becomes so much more complete. Okay, this loss of restrictiveness is expected because we're combining the 2 different stages, so we're guaranteed to make the model more flexible. So this is expected, but what's surprising is that the restrictiveness does not drop too much, but the completeness increases a lot. So the takeaway we're getting from here is that although this cognitive imprecision is insufficient, it's sufficient to explain belief updating in simple environments. Now, in more complex environments, simplifying the environment through representativeness is really essential. And so this interaction is what's making the 2-stage model really powerful. Okay, so I don't have much time, so I'm going to skip the structured estimation. But so far, I hope that I've convinced you that our 2-stage model, it explains the data really well. But the remaining question is, how can we be sure that this results are actually driven by the psychological mechanisms that I've put forward, by channel attention and cognitive imprecision? It could be that we just we just happen to have some quantitative predictions that work really well, but we're not capturing the core mechanism. Right. So in this last part of results, we study the attentional mechanism directly. And importantly, we will be holding the information environment as constant. We will just vary how people shift their attention. So any effect here provide direct causal evidence for attention. In the first experiment, we measure and we limit attention. So here we adopt the mouse-led paradigm to track what people pay attention to. And this paradigm has been first used by Payne, Batman, and Johnson in 1988 to track and measure attention. So the core idea behind that is that in order to know what things you're paying attention to, we keep track of what things you are clicking at first. So the idea is that the first thing that you click on is the thing that you attend to first. In our previous treatment, we just have a box below each of the states for you to enter your beliefs. But here, our participants need to click on a button before so that a box will pop up and they can enter their beliefs. Okay, so in that way, we can track which things they click on first. So one key insight from this literature is that this paradigm itself requires attention. So it's likely that so it further limits the attention stock. And if our hypothesis is true, then this is going to lead to more overreaction, right? So now let's look at which states our participants click on at first. So it turns out that they are much more likely to click on the representative state. State 1 gets the most clicks if it is most representative. State 5 gets the most clicks if it's the most representative. In addition, if we impose this paradigm, we have more overreaction as consistent with our theory. In the second experiment, we study the role of representativeness by turning off representativeness as a salience cue. So here, the expectation is that the agent's attention is no longer driven by representativeness. Now, how do we do that? So here, participants do not immediately see the composition of balls in each of the urns, or here we say bags, but they need to click on this box to review the composition of the balls in each of these urns, and then enter their beliefs. Okay, so this feature is going to generate uncertainty over which state is representative ex ante, because I don't know which bag has contained the most red or blue balls. So this makes it more difficult to channel their initial attention to representative state. Indeed, when representativeness is turned off in this fashion, attention is no longer channeled to the representative state. Instead, as predicted, this is the percent of first clicks on each state. As predicted, their first clicks are pretty much evenly distributed across all of the states, regardless of the signal realization. So here, because no state is salient, right, they're all ex ante looking similar, their attention is channeled as if random. So, but although the distribution of attention is random, as predicted by our theory, still people overweight the most attended state. So if you look at the difference between the subjective posterior and the basal posterior, people overweight the state that they click on the first, and underweight all the other states. So now, because attention is random, now 80% of the time, you're overweighting something, but 80% of the time, 4 out of 5 times, you're overweighting the state that is not the most representative, right? So on average, our model would predict overall underreaction. So this is confirmed by looking at the overreaction ratio. We have a complete reversal from overreaction to underreaction when we turn off representativeness as a salience cue. And this is quite remarkable because remember, this is an environment with 5 states where we have a really robustly observed overreaction. But now, just by changing how people shift their attention, we can completely change the patterns to underreaction. Okay, now in the last experiment, we study if there are other things other than representativeness that can drive people's attention. So for example, in particular, we introduce visual salience cues by just highlighting some states in yellow. We introduce goal-directed salience cue by incentivizing a guess for a particular state. And so visual salience is still the top-down salience cue. Visual salience is still a bottom-up salience cue, but goal-directed is closer to like rationing attention. It's a top-down salience cue. So the result is that when representativeness is suppressed, as before, this alternative salience cues, they also lead to overweighting of the salient state. And if the salient state is the most representative state, this also leads to overreaction. So the overreaction ratio is quite similar. Okay, so this means that these alternative salience cues, they play a similar role as representativeness in driving attention. But this happens only when representativeness is suppressed. When representativeness is not suppressed, these alternative salience cues are pretty much dominated by representativeness. Why? So we find that applying these alternative salience cues to the least representative state, so going in the opposite direction of representativeness, this does not change the overreaction ratio that much. We still have overreaction. We still have the overreaction that likely arises because of representativeness. So we believe that these results, they tell us the importance of saying representativeness as a particular salience cue in belief updating. All right, so I'm out of time, so I'm not going to talk through the extensions, let me summarize the paper here. So in this paper, we develop a belief updating framework that incorporates multiple psychological mechanisms. And our model predicts a rich pattern of under and overreaction depending on the information structure. And we provide empirical support for these predictions, including evidence, direct evidence for the attention channel. And together, they point to methodology for a unified approach to modeling multiple psychological mechanisms simultaneously, because studying the interaction between them, this could help us rationalize prior findings on over and underreaction across a variety of domains. So thank you a lot for your time, and I look forward to knowing your questions. Thanks very much.
So I have a question. I'd like to know what's your findings, revelation for our own decision.
For our own decision,
Yeah.
I guess yes. So I guess because it's for our own decision, our decision pretty much happen in the real world as opposed in the lab, right? And in the real world, there's much more complexity. For which we could have a tendency to jump just right to the conclusion that we think is right too much. So in other words, we're overreacting to like very noisy signals, and we're jumping to the conclusion, we're jumping to believing, attaching too high probability to those extreme states that could be like conspiracy theories or very extreme positions. So I guess the lessons for individual decision making would be to be very cautious when you take that, before you take that leap, especially if the signal is quite noisy. I'm not sure if that answers your question.
Yeah, I just would like to know how we can relate all your findings to our own personal life.
That's very, I think it's very easy to find examples of that, right? So let's say you're, say in the US, okay, you want to know which president candidate is better. And sometimes the president the candidate does something that's really irrelevant, like frying fries in McDonald's. That's a really noisy signal of the president's quality, but you jump all the way to say, oh, this is a very and there is a bunch of possible states that, you know, the underlying quality of the president candidate, but you jump all the way to say, oh, this must be the best president because he fries in McDonald's. So I think we have a lot of empirical evidence for that.
Yeah, so that also provides you see possibly you see let us know that how this information might be manipulated to influence people's decisions.
Yeah, quite possibly. So maybe, so I'm just like brainstorming here, because we have people underreacting for simple state space and overreacting for complex state space. Maybe one way to induce like a overly strong prediction would be to expand the state space. So to create, for example, you have two products to choose from, but now you have 3 products to choose from, and maybe in that case you will be overreacting to any information provided and just jump to the particular product that other people want you to buy, for example.
Mm-hmm. Thank you.
Thank you.
Hi, Cuimin. Also got a quick question. So I find one of the findings really, really intriguing. If I'm not mistaken, when you go in your state space, when you go from 2 states to 3 states, you see this, you know, fundamental change, right? Going from underreaction to overreaction. And you also show on the graph that when you go from 2 states to 3 states, 4 states, 5 states, up to 11 states, basically, you know, no matter how many states you have down the road, there's only marginal increase in the extent or the degree of overreaction. And I'm not too sure, but on the graph, it seems to be kind of linear increasing when you increase the states all the way up to 11. So I'm quite intrigued by this finding. So, I mean, in a way, you know, like it doesn't really matter once you go to 3 states, no matter if you get 4 or 5 or 7. I mean, it seems to matter really little, right? So
Yeah.
what's behind these findings? It's quite interesting.
Right. So I think there are two things behind this. The first is that there is psychological evidence that how many objects that you can simultaneously pay attention to. So according to psychological evidence, is tops like 4 to 5 objects at the same time. So if you have 2 states, then you keep track of maybe 4 objects at the same time, the prior conditional probabilities, right? But if you have 3 states, then that just like suddenly exceed the amount of the number of things that we can attend to simultaneously. So I think that's what's driving this shift here. The other comment that I have is that this 3 state is actually also so we have to combine with the other prediction that you overreact to noisier signals. So one feature of this 3 state as compared to 2 state is that we're essentially making the signal noisier because we're adding the middle state 0.5, which is a totally uninformative state, right? So in other words, we're making the state the signal so much more uninformative. So I think that's 2 reasons. There are 2 reasons that's driving this complete shift.
Right. And is it just on the graph? But it looks to me that this increase is kind of linear.
Yeah, maybe sort of. I think that's a stretch. So we only have this 5 conditions. We don't have like 6, 7, 8, 10. So maybe we can in the future, maybe we can look at that. But yeah, I'm not so sure about that.
Okay, thank you.
Thank you.
Hi, Cuimin. Thanks for the talk. Quick question. So I'm wondering if we allow for signal space to be larger, what from your conjecture, like would the model say?
Yeah, that's a great question. So that's actually one of the extensions that we have, but we only look at we only go in this direction for a little bit. So sorry. So in our main model, we have a binary good news or bad news structure, right? So a way to extend that would be to look at more general signal structures, for example, with more than 2 signal realizations, with a good signal structure that's not a good news or bad news structure. So which means the conditional probability of seeing a signal is not changing monotonely with the state. So in that, we have a three state, 3 signal design. And it has the feature that the middle state could also be representative. So we can have a middle, like a green signal, and the middle urn contains the most green balls. And in that case, we confirm the pattern that people still overweight salient states. So if it's a red state, overweight urn A. If it's a green state, overweight urn B. If it's the blue signal, overweight urn C. But because the salient state may not be the most representative state, now whether people overreact or underreact, this is going to depend on fine details of the parameter. Because if you're overrating the middle state, it's unclear whether you're pointing towards overreaction or underreaction, right? So I guess the takeaway from here is that the general conceptual framework applies. It tells us which things that you are paying attention to, but the predictions on under overreaction we have to look at it, the parameter structure more closely. Thank you so much for the question.
I think your findings are quite interesting, and I was wondering, you said your framework incorporates some psychological mechanisms. So, I was wondering, which or what kind of psychological mechanism inspire you to do this framework?
Right. So the first one is the limits on working memory constraint and the tendency of to simplify the information environment with that constraint. And that results in the use of representativeness heuristic to simplify the information environment. And the second one is that people are noisy in their perception because they are the processing constraint. And so they incorporate noise in their decision making. And this we also observe noise if we look at each individual's answers. So that's the two mechanisms that's more or less like directly motivate our two-stage model. So mental representation and also processing.
Okay, thank you very much.
Thank you.
Any other questions? Okay, great. Since we've already run out of time, I'm sorry to interrupt, and we should stop here. And thanks a lot for attending today's webinar. And thank you so much again, Dr. Ba, for bringing us this fantastic talk.
Thank you so much for paying attention here, especially given that attention is so constrained. Thank you so much. Appreciate your time.